Yeah. So, okay, so remember what we're doing? We're talking about the fundamental theorem of calculus, what's generally called the second fundamental theorem of calculus, even though we're encountering it first. Okay, so this is, the sort of the climax of the course, in fact. The fundamental theorem of calculus. Number 2. And it goes like this. If you have a continuous function on AB, and you have an antiderivative, any antiderivative, right? And any antiderivative of some function little f on the interior, then it turns out that you can calculate the integral of little f just by taking by evaluating the antiderivative and taking the difference at the endpoints. So this just seems sort of startling, right? You can tell about this function, the integral of this function, just by evaluating a function on the endpoints. Okay. When you go up to take calculus in several variables, you'll see that there are analogous things where, for example, somebody asks you for the area of a region in space. So you have something in the plane, you have some region in the plane, and you're looking for the area of that region, or you're looking for some integral over that region. Let's just say you're looking for the area of that region. It turns out that there's something called a line integral, and you can just evaluate the line integral over the boundary here, and then get the area on the interior. This is sort of the analog, the multi-dimensional, several variable analog of this statement. And actually, after this theorem came out, this is something called Green's theorem. Engineers started making devices called planimeters. Planimeters, which are just these things with gears, and you can run them over the edge of if somebody draws something on the table and says what's the area of it, you can run the planimeter over the edge of the thing, and it will, using its gears, calculate some sort of integral and tell you what the area is on the interior. I have one in my office. I got one on eBay a few years back. They're not expensive. The old ones from the late 19th century are expensive, but mine is from like 1940 or something. Anyway, so they have these things, and nowadays they have them digital, so that they calculate the integral digitally as it goes around. But it actually can be done with just gears. Okay, so this is just the beginning of a sequence of theorems, all which talk about evaluating something on the interior by evaluating something related on the boundary. Okay, so you have this. Here is your interval. Here's your interval, and you'd like to know something about this integral on the interior. But it turns out that it's equivalent to evaluating this related guy on the boundary, on the edges of it. Okay. So this is great. Like we said before, this relieves us of the need of running through the process of Riemann integrals, right? Because otherwise, to evaluate an integral, how do you do it? Well, you have to take your Riemann sums. You have to take your Riemann sums at every scale, right? Your first one, your second Riemann sum, your third, your fourth, blah blah blah, and find out what the Riemann sums are based on those partitions, and then let the partition go to infinity, and then you can figure it out. We did it once, right? And it was I think a great relief to see that you could do the same thing by taking the antiderivative and evaluating the difference at the endpoints. Okay, so here's the second fundamental theorem of calculus. Let's see why it's true. Okay, why? Why does this work? Why does this happen? And we're going to give one argument right now, and we'll give another argument later. This is the one. I'm not sure I like this one so much, but it's kind of cool. So here's the argument that shows us how this thing works. Okay. Say okay. Here's your function. Here's your continuous function. Take a Riemann sum. So take a partition. Take a partition. X naught to xn of a. Okay. So take a partition where all the intervals are the same width. Okay, I think that. Yeah. Right. So delta x is again going to be b minus a over capital N. Right. So the width. This is x naught, x1, x2, xn, and the width of these guys is we're going to call delta x. Okay. Okay. So now what we're going to do is apply the mean value theorem. Apply the mean value theorem. Apply the mean value theorem to capital F on each interval, xi minus 1, xi. Okay, so from I equals 1 up to n. Okay, so we take each interval, right? X0, x1, x1, x2, x2, x3, x3, x4, etc., etc. And we apply the mean value theorem to it. What does the mean value theorem say? Somebody tell me. Does anyone remember the mean value theorem? The most important theorem in differential calculus? Can anyone roughly tell me what the mean value theorem says? After Thanksgiving? Michelle. Okay.
If it's continuous on a variable differentiable, then there's this f prime c equal f of b minus f of a over b minus a. Very good, very good.
So as long as this guy is differentiable on the interior of the interval, and it's differentiable because its derivative is little f, right? And it's continuous on the whole interval, and it is. Then you know that there exists a point. Let's call it S sub I in the interior xi minus 1 xi, where f prime of si equals f of xi minus f of x sub I minus 1 over x sub I minus x sub I minus 1. That's what the mean value theorem will tell us. Right? In each of these intervals, we apply the mean value theorem to each interval, each subinterval here. Okay. Any questions? Okay. Any questions on why that's what the mean value theorem says, right? There's going to be some point where the instantaneous slope equals the average change over the interval. Rachel.
Okay, so what are the xi's? Are they like the different points that are at the end of each partition?
That's right, that's right. So for each interval, when I equals 1, we're talking about x0, x1, right? x1 minus 1, comma x1. When I equals 2, we mean x1, comma x2, right? Because that will be x2 minus 1, x2, and then all the way up to xn minus 1, comma xn.
Okay.
Right? So we're applying the mean value theorem to each of these intervals. X0, x1, this interval, this interval, this interval, da 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 da, and this interval. Okay, so apply the mean value theorem to each interval. Okay, and the mean value theorem tells us that that in each point, in each interval, there's some s. There's some s. There's going to be an s1 here. There's going to be an s2 here, s3 here. There's some sample point where this happens. Okay. And is that clear? Anyone confused? Okay. So let's see. This f prime is what? What's f prime? Capital F was chosen in a special way so that capital F prime is little f, right? So this is little f, right? So that tells us that little f si equals capital F xi minus x minus 1. And I'm going to move, I'm going to multiply both sides by this xi minus 1. Okay, so that's the same thing as, well, let me just write here, xi minus 1. Okay, and then I'm going to write each of these things, each of these xi minus 1, I'm going to rewrite it as just delta x, right? Because they're all the same width. They're all the same width, delta x. So we're good. X. Delta x equals xi minus and this is true for I equals 1 and okay, everyone all right? Any questions, Sharon?
Why did you multiply x of y to f of x?
You'll see why in a second. I wonder if anyone can guess what I'm going to do next. What am I going to, can anyone see what I'm going to do next?
Take a limit.
Not yet. I will eventually take a limit. Okay, don't worry. So that's true for every interval, right? For every interval, f at the endpoints, the difference of f at the endpoints equals little f at some sample point inside times delta x. So I'm gonna. That's true for I equals 1, 2, 3, 4. Let me write it out. So like f of there's an s1, so that this is true. There's an s2. Where this is true. There's an S3 where blah, 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 all the way up to Sn. So I'm just rewriting that last thing for all the way out. Okay. So all I'm doing is writing this thing out for every I, right? I've written the same thing twice, just expanded it. Okay? Sure.
Isn't that the part in the Riemann sense?
Yeah, exactly. Yeah, it's part of the thing in the Riemann sum. So if I sum over all of them, right? If I sum over all of these guys, I'm going to sum the left side. Fsi equal to x as I goes from 1 to n. Then this thing on the left is a Riemann sum. It is an nth Riemann sum for the integral of f dx on here. Yeah, I should give you a point for that, Sharon, on the points. Okay. And so when we sum all these guys on the left, we get this. And what about when we sum on the right? What do you get? What do you get when you sum the right? everything on the right, f2 minus x1, f3 minus x2, f4 minus x3, f5 minus x4, blah, 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 xn, fxn minus fxn minus 1. You see what happens? Do you see what happens? It collapses, right? It's what's called a telescoping sum, right? We have f2 minus x1, right? Minus x2 plus x3 minus fx3 plus fx4, right? All the way down to minus fxn minus 1 plus fxn, right? And you see that, let me move this way. Minus fx1 plus fx2, right? You see what happens, right? It collapses in, right? And you end up with fxn minus fx1. Right? This is what's called a telescoping sum. Okay? fxn is b, right? xn is b, and x1 is a. Fx0, sorry, I should have started from 0. Right, there should be a zero term here. Sorry. Fx. Sorry, I messed up a little bit. This should actually be x1 minus x0. Sorry. There should be 2 minus x1. 0. Anyway, this should be x0. Now it's right. So I just added in this and fixed these guys. Okay. So what do you see? You see that you have a bunch of Riemann sums. You have the nth Riemann sum for this integral, and it equals f of b minus f of a, right? And I can do this for any n, right? I could do this for a tenth. I could divide the partition into 10 pieces, and what am I going to get? I'm going to get f of b minus f of a, capital F of b minus capital F of a. I can do it into a billion pieces. I'm going to get f of b minus f of a, blah, blah, blah. So I take the limit, right? So I take the limit as n goes to infinity, and you get that the integral, right, on the left-hand side, you're going to get the integral. Your function is integrable, so this limit of Riemann sums is going to turn into the integral, the definite integral. And on the right, the right stays still the whole time. Right? And so you get the theorem. The definite integral of this guy, little f, is the difference of any antiderivative at the endpoints. Any questions? Any questions?
It's beautiful.
Great. Yeah, amazing, right? Amazing. Right. So this is great. I said this in previous classes that once I was having lunch with my postdoc advisor, and he said, if you could plagiarize any result throughout history, what result would you put your name on? And I said, because the field of study that I'm in is something called harmonic analysis, and the key tool in harmonic analysis is something called the Calderon-Zygmunt decomposition. And I said, the Calderon-Zygmunt decomposition. And he said, you were thinking too small. I would put my name on a fundamental theorem of calculus. It's like, oh. Yeah, that's right. Yeah, definitely. That would be the right move to make. If you wanted your name to last throughout time, you put your name on a fundamental theorem of calculus. So this is okay. So this is one way of thinking about the fundamental theorem of calculus. The proof of this, the proof, as you see, really relies on the mean value theorem. Okay. Later on, we'll do a completely different way. We'll see a completely different way of seeing it, which will go a different route. Okay. Okay, everyone. Any questions on this? It's pretty important. Right. You take your interval, you divide it up into n equal subintervals, and then you apply the mean value theorem to capital F. Right. You apply the mean value theorem to the antiderivative. Right. On each subinterval, and you see what that tells you. That tells you that on each of the subintervals you have something that looks sort of like a baby fundamental theorem of calculus, right? It says that well, you can take f at a single point and multiply by the width of the base. You can take, so here's your xi minus 1, xi. It says that there's some point there. There is some point in there where the rectangle you get, the approximating rectangle you get, the area of that is the difference of the antiderivative at the endpoints. So this isn't the full-blown fundamental theorem of calculus. This is some sort of wimpy version of it. Okay. Right? So the mean value theorem gives you these, sort of wimpy fundamental theorems of calculus on each subinterval. And then you say, well, I'm going to sum them all together, and I'm going to take the limit. Right? And when you sum them all together, you get the Riemann sum for the whole thing. You get some fact about the Riemann sum for the whole definite integral, and then you take the limit, and you get the definite integral, and that wimpy thing turns into the actual. Okay. So that's that. Yeah. So the next stuff we're going to do, I'm afraid, is kind of a downer compared to what we've just seen. It's very simple stuff. Okay. So 5.3 basic properties of integrals. So these are things that are kind of obvious. Well, some of them are kind of obvious. Okay. And further, it's just basically a list of things. Okay. So some simple ones. One, the integral from a to a of f of x dx is going to be what? 10? Somebody said it? 0, right? It would be 0. Right? Why? Why? Because when you take the Riemann sum, you're going to be taking a Riemann sum where the length of the subinterval is 0, right? Right. So you're going to be multiplying. You have a rectangle with a height, but no base, right? A 0 with base. Number 2, integral from a to b of 1 dx. What's that? If I integrate the number 1, Leanna?
1?
No.
1 times b minus a.
1 times b minus a, yeah. So you get 1 times b minus a. In other words, b minus a. Right? In other words, you get the length of AB. Right? You see, you've got A, B, right? You're integrating the number, you're integrating the height 1, right? What are you going to get? Right? When you take your sum intervals, right? You're going to get the rectangles, but your rectangles are all going to be the same, and all of your Riemann sums are going to be perfect, right? Because the thing that you're approximating is a rectangle, right? And so what you're going to end up with is 1 times the width of the base, which is b minus a. So you get the length of AB by integrating 1 over it. Keep this one in mind. For some reason, students always mess this one up later on. They don't understand that you can get a length by integrating the number 1 over it. In higher dimensions, if you integrated the number 1, if you integrated a height 1 over this thing, then you would get the area. You would get the area of the object. The integral from a to b and from b to c is going to be equal to what? The integral from a to c. And so all this is saying is that, right, you have 3 points a, b, c, right, and you have one function like this, and the integral over this part plus the integral over this part is the integral over the whole integral AC. Okay. Other things. Here's something we're just going to take as a definition. The integral of over b to a, we're going to define as minus the integral from a to b. Okay, so it's permissible to take integrals in the reverse direction. Okay, so if a is here and b is here, it's still okay to talk about the integral from b to a. So it'll be in the reverse direction. But in that case, we're gonna put a negative sign on it. So you can just take that as a convention, but it's a convention. It's the convention that works out basically. Okay. Okay. So here is a really important property. Actually, it's called linearity. And it comes in 2 parts. The first is that if you take the integral of a sum, if you have 2 functions and you sum them and then you take their integral, then that's going to be the same thing as the integral of the sum. And then the second part is if you have a number, alpha, so let alpha be a real number, if you integrate some multiple of your function from a to b, then that's the same thing as the integral as alpha times the integral. Okay. So, for example, if I'm asking you to integrate, say, pi times x over the integral over 1 to 2, you can say, well, I can pull the pi out. I get 1 to 2 x dx. Right? And then this will just be pi times x cubed 3, 1, 2. Right? That is pi times 8 over 3 minus 1 over 3. Right? So you can pull constants out. Pull constants out of integrals. So this is again commutation. Something about commutation, right? The integral of a sum is the sum of the integrals, right? You can either do the integral. You can sum first and then integrate, or you can integrate the sums. Right? Or you can get the integrals of the sums. Similarly here, you can either multiply your function by a number and then integrate, or you can integrate and then multiply by that number. So this is actually pretty important. Okay. So So just to illustrate these properties, and this is sort of a contrived exercise. So there are a bunch of sort of contrived exercises in this section, and they're sort of like this. Somebody says, suppose I know that the integral of your function from 2 to 12 is negative 6, and the integral from 2 to 6 is negative 12, right? What is the integral from 6 to 12? So just look at it for 10 seconds. What's the answer? Oh, 6, right? 6. Right? Because you know that the integral from 2 to 6 plus the integral from 6 to 12 will be the integral from 2 to 12. Right? So this plus this number had better be this number. Okay. Let's see, maybe a more sophisticated one. The integral from 0 to 4 of twice f of x minus x squared dx equals 6. What is the integral from f of 0 to 4 of f? Okay, take 1 minute and see if you can do it. Okay, somebody tell me, even if you haven't done it, tell me how to do it. What should I do? Well, this thing is 0 to 4, 2fx minus x squared dx. Does anyone see how to do it? Ellen?
Do you split them out?
Yeah, let's. So we know that this thing, 2fx dx, the integral of negative x squared dx 0 to 4 is 6. Right? And then we can, what? We can solve the second one, right? Let's pull the minus sign out. Okay. So here we get x cubed over 3 between 0 and 4. We get minus that. And here, what should we do with this one? We'll pull the 2 out. Right? So we get 2 x dx. Right? So we get 6 equals twice the integral from 0 to 4 of f of x dx minus, and that's going to be 64 thirds minus 0. Right. So, right. And then you see this is basically back to junior high school algebra. Right. This is the thing you're looking for, right? And so you've got 6 equals 2 twice your unknown minus this constant. Right? And so you move the constants over to the other side and then divide by 2. Okay, so return to junior high school. Okay. Any questions? Right. All we're doing is using the basic properties of the definite integral. Okay. The last one, I'll just set it up. Number 21 goes like this. The integral from a to b of f minus 3g equals 3. The integral of negative 6g plus 9f equals 6 from a to b. Okay. And I should write the x and the dx and stuff, but I'll be lazy. Okay. And they say, the question is, what are the integral of f from a to b and the integral of g from a to b? Okay. But again, you see that this is basically, again, a junior high school problem. Because you split this thing up, you say, well, the integral from a to b of f minus 3 times the integral of g from a to b equals the integral of negative 6g from a to b plus 9 times the integral of f from a to b equals 6, right? And now it really looks like you've come back to junior high, right? You've got 2 unknowns. You got f, the integral of f, and you have the integral of g, and you have, again, your first unknown minus 3 times your second, negative 6 times your second unknown plus 9 times your first equals 3 and 6 respectively. And it's again a junior high school problem. Okay. Is it clear? Is that clear? That all you're doing is using the properties of integration and then changing back to an elementary algebra problem. Okay, that's it for today.